Okay, so I just finished day 3, part 2 of Advent of Code, and this ended up being kind of a number theory problem. Just to sum it up, essentially for part 2, they flip the rules on us. So instead of the x meaning that the bus is not in service, you actually have to account for this x value. So the first bus ID departs at the time, you're looking for a time t, where the earliest timestamp, t is the earliest timestamp such that the first bus ID departs at that time, and then the second one departs 1 minute later, and you're still constrained by this bus runs every 7 minutes, this one's every 13 minutes. So these buses all run every 7, every 13, every 59, and then you have to account for these as constraints. And so there is no constraint on buses leaving at minute 0, 1, 2 minutes after t, and nor is there for 3 minutes, but then this bus 59 needs to run 4 minutes after time t. And so you're looking for this time where the earliest time that all of these overlap. So you can see here, time t, this whatever value here, 1,068,781, is when bus 7 runs at that time. Bus 13 is a minute later. Bus 59 is 2 minutes later because it's in this array at 2 positions after, or I guess it's 3 minutes. So it's position 3 after 13. And then bus 31, same deal. There's an x in between, so you have to account for the x, but you can ignore it. You just have to account for the position of the index of 31. And so in this little duration here, starting at this time, these buses run in this order. So initially I tried to brute force it. I was able to brute force these ones. I essentially just went through like one by one every time, and then I ran a test on the constraints. But by the time the input that they give us is way too complex to take that kind of brute force solution to it. I ran my code for 20 minutes, didn't spit out anything. It pegged my CPU, and so I knew I had to take a different approach. And after reading around for a bit, there's this theory called the Chinese Remainder Theorem. Sounds a little racist to me. I don't know. I'm sure that the Chinese came up with more theorems than just this one remainder theorem. We don't call the Pythagorean theorem the Greek theorem, or wherever Pythagoras was from. But that aside, this is apparently like a well-known cryptographic theorem, and I don't totally understand the reasoning behind why it works, but essentially you can have these equivalences, or congruences, I guess, is what they call them. So if you have a number x such that x divided by 2 has a remainder of 5, x divided by 3 has a remainder of 7, then you can use this theorem to solve that. And the full theorem is basically this a, let me see if I can get this right. I think this a sub I is the modulus. This b sub I is the partial sum, and then I guess I should start over. See if I can find the Wikipedia article on it. I found several really useful YouTube videos that go through some simple problems using Chinese Remainder Theorem. There's a Wikipedia page. It's pretty technical, and I wasn't able to decipher it very well. But essentially, here's these congruences. If x is a1, and then the remainder is n1, and these are all true, then you can basically use a sum to compute what x is. And one thing I learned is that if you have this list of congruences, basically this congruence is this value, so that would be a1 in this case, and then the mod, which is n1 in this case. You can take this product of all of those numbers, of all the moduli, and it forms an upper bound of solutions. So whatever your solution is going to be will be somewhere between 1 and that product. And so that it puts an upper bound on how big your solution can be. And then you basically compute this sum using this formula that they give you. So I pass in this list of congruences, and then the way that I built that list is I put this I value, which is the index of the array, and then I had the mod be the value. For some reason, a lot of this is going to be kind of hand wavy because I don't totally understand how this theorem works or why. But I plugged in the index values for this. So this would be like 0 in this case. This value would be, given this input, say, this congruences would be like 0, and the mod would be 67. And then there wouldn't be anything here because I ignore the x's. This would be 2, and then mod 7, because 7 is in the 2 index here. So essentially, I created this solver, given this list of congruences, and then it computes the product by multiplying together the mods, the moduli here. And then the sum is this is the Chinese Remainder Theorem. The sum is a product of, it's a sum of all the products of the partial product, which is this overall product, divided out by the individual mod. So this partial product is the product divided by the mod. The inverse is the multiplicative inverse, which is, there's some Euclidean values for that. So you're basically solving for this modulus value that makes this return something equivalent to this or 1. So the inverse is always going to be some integer between 1 and the partial product here as your upper bound. Again, don't really know why. It's part of the theorem. And so the theorem says, like, if you multiply all these together and then you multiply the value here, which in this case, I guess this would always be 0? Or no, it would be the index, right? Then that sum mod the product, because if you're guaranteed to find the solution between 1 and the product. So you mod the product so you get the remainder of whatever's left over, and that gives you your solution. What I found with mine was I was running these tests and I realized that I'm not, like, in my tests when I was solving for some of these values that they gave me on YouTube, I found that I was getting the result, but apparently there's some kind of inversion that's happening by me setting the value to the mod here as I'm going through the inputs, where apparently I'm not actually solving for the sum. And so I realized that a lot of the answers that I was getting had this offset from the right answer that they wanted. And I don't fully understand why. I might dive in if I get a chance and try to figure out, like, it's something to do with the input that I'm giving. Like, the way that I'm setting up these congruences and these offsets is when I put it in this solver, I'm getting something that is an offset of this sum from the product. I don't know why, but I noticed that as I was going through one by one and computing these, that the result I was getting was always like a certain number off from this. And ultimately after I solved this, I lost my train of thought. Ultimately, like, this solver was really fast. It just chops through. If you run all of these, previously when my brute force solution would take several minutes to run on a lot of these inputs, this just goes right through. So yeah, you can see that ran in 77 milliseconds to solve all of these congruences. So it's effective. It's much more efficient than whatever the brute force algorithm that I was using. I just don't totally understand it. I don't like that I don't understand it. I wish I had more time to dive into it and really grok it better. But I did in my code include some links to some YouTube videos that you can watch to get a better understanding of it, and I'll probably revisit it. It sounds like I'd never heard of this before, but it sounds like it's a pretty important algorithm that's used quite a bit in cryptography, and it's yeah, I wasn't aware of it, but I started reading through some message threads and stuff on Reddit, and I came across it as a lot of people read this problem and immediately thought of that theorem. So I wish that I could explain it better, but essentially I just took the formula and I created some congruences in this data structure, plugged in the formula, and then I got the answer. So I'll include some of those YouTube videos that I used to understand it in the description for this video. So this is going to be a relatively short video. This one took me a while. This was a pretty challenging part 2, significantly harder than the part 1 for this day, but I don't know, I kind of like stuff like this. Like it forces me to dive into these kind of fundamentals and algorithms and number theorems that I wouldn't have encountered in my day-to-day job and my day-to-day work. So I enjoyed it as much of a headache as it was solving this one. It was fun in its own way. So it was type 2 fun is what I would say. So thank you for watching. I hope this was helpful, or at least steered you in the right direction, and I will see you in the next one.